Thank you, Ed, very much. You know, I love BART. I think it's a very, very powerful, very useful prediction tool. And now I learned there's also a causal version of it, so I should really take a look. The next speaker is going to be Hedibert Lopes from the University of Arizona and INSPER in Brazil. Let's welcome Hedgie.
First of all, I want to thank the organizers, particularly Edo, for giving me the chance to talk about some of our work on factor models. And it's not fair to talk right after Ed because I have so many questions for him. I guess we'll do it later, right? This part of monotonicity and combining the ups and downs will be very valuable when you do BART for time series, which is something that I'm starting working with Rob McCulloch. And I think that will be very important, especially when you have this sine cosines modeling periodicity and things like that, like someone talked earlier on. So we all are a big family. We all work on relatively similar projects. And as Edo just mentioned, I have a master's student that went to work at Austin doing Bayesian BART, causal BART as well. And I have a PhD student still from Brazil doing also causal BART with regression discontinuity design, which is something that is pretty famous in econometrics. So there are lots of things to explore there. But this is not what I'm going to talk about today. What I decided to talk about, it could have been something else, but this is something that excites me right now because Enrique Bolfarini just defended his PhD thesis. For those who are old enough here in the statistics, know the Bolfarini last name is a Brazilian, one of the most important Brazilian statisticians who passed away like a few months ago, has been battling Parkinson's for 10 years. And I had the pleasure to work with his son, and you can imagine like being the son of someone with such a powerful name. And Enrique came not knowing exactly what he wanted to do, and we worked for a couple of years, and now he finished his PhD thesis a week ago, and he started a postdoc with Carlos Carvalho. Everyone knows Carlos. Carlos was also my first master's student back in Brazil after I finished my PhD at Duke. And of course, now Jared is one of the rising stars in this whole area of causal BART and in more modern Bayesian applications. So what Enrique did here was basically looked at this DSS, this decoupling, shrinking, and selection in the setting of is that like a movie or is it just me? The setting of factor models. So in these slides, I have like 100 slides. I was supposed to talk about mixtures, but I won't. So don't worry, it's not going to take 1,000 slides. How do I move this forward? Hmm? The other one? This one? Oh. So I have to hold this too? Okay. So the topic of variable selection is something that it's everyone's attention these days, Bayesians or non-Bayesians. And after the very famous work of Lasso and related tools for regression sparsity approach, we Bayesians just said that, well, look, we do shrinkage forever, and then there is like a plethora of priors inducing sparsity in the literature. I guess the most famous ones are the horseshoe, the Bayesian lasso. There are even like a 3 gamma kind of prior for inducing zero coefficients in a regression. And that's what these guys did for the regression setup. What we're going to do here, following this decoupling, shrinkage, and selection, it's basically what the title says. We separate shrinkage from selection. And here, shrinkage will be essentially fitting, model fitting, and selection will be like a decision step after the model fitting. So we go back to basic approach, looking at, for instance, this 1968 paper by Dennis Lindley, sorry, where he talks about not only priors and likelihoods or posteriors, but also the utility function. So that's something that we, as a Bayesian, learn when we do statistical decision analysis. And one setup is to imagine that what you want to do is, for a particular decision variable, you want to maximize the posterior predictive expectation of a utility function subject to some cost function. Here is already in a very particular case. You can make this more general. You can put the cost inside the utility function. But for the things that we're going to present, it will be easier just to look that way. And if you go back to Lindley's paper, which is a Series B discussed paper, has a lot of discussion, interesting discussion about how you play around with these components. And for us who do Bayesian statistics, posterior predictive is usually like a byproduct of your, MCMC or any kind of scheme for inference. Okay. So the paper that Richard, my new colleague, and Carlos Carvalho wrote back in 2015, I think, it's called Decoupling, Shuriken and Selection in Bayesian Linear Models. It's a review paper, a JASA paper. And basically what they do is they separate, this loss function. Now they change to loss instead of a utility, and then move to the decision step, the step of optimizing over some, selection step. In other words, you don't have to, you could, but you don't have to impose in your prior some sort of sparsity approach. You can delay that to the posterior predictive, which in this case is the moment you make the decision action, which is maximize or minimize this function. The way it's written here, it looks like the usual penalization setup, but this lambda didn't necessarily need to be outside here. It could be indexing P, so it could be anything, not necessarily a multiplication function. Actually, in the paper and his thesis, he doesn't impose that. Okay. So to make things a little bit more obvious, so what we do is we take the expectation with respect to the posterior predictive. So what would have been the new observation, new condition on the existing one. So here you're integrating out with respect to all the unknowns within a particular model. So this is a function of the posterior of the unknowns given the data, the actual observed data. So in this way, if you try to make a connection to time series or prediction, so we're predicting the y tilde given y. So what is the next observation? What would be, if there is a time component here, so it would be what is the distribution of yt plus 1 given y1 through yt. So we take into account the uncertainty about everything that we don't know, conditioning on a combination of prior and likelihood. So once we have this predictive, and not always we're going to have it in closed form. Once we have this predictive, we just minimize with respect to this posterior predictive, we minimize the loss function, and that's where the potential sparsity comes in. Okay. So essentially, what we do is decision analysis-based method. It's not necessarily important to pick a prior at the beginning. You can use your more generic prior. You can be like non-informative prior or a prior that do impose some shrinkage, not a lot of selection, for instance. And then you defer to the decision analysis, the step where you do the selection. So the selection is decoupled from the shrinkage. So it's just a fancy name that these guys invented, and I'm just using that. There are a couple of other papers out there already that implemented this in other setups, like one that I like, and it's relatively similar in some ways to the work that Henrique did, is this one in graphical models. And the Gaussian process here is a more recent one. Okay. So in a factor analysis, what we're going to do is, well, there are two things that if you are interested in factor models, two things that come to mind in general, at least in my mind, is the number of factors, what they mean, how they come up into the analysis, and also once you figure out the number of factors, maybe you don't, what are the weights of those factors? And the weights of those factors are the loading matrix, are all in the loading matrix. So sparsity in the loading matrix is something that we do. So I have papers, and a bunch of other people have papers that induce sparsity through the prior in-factor model, so it doesn't disentangle these two things. And what we're going to do here, and that's the main theme of this talk, is to fit what we call a saturated factor model, and then we use the DSS idea, the decoupling, shrinkage, and selection, to pick the number of factors or to observe how posterior inference varies according to the number of factors, and if you have shrinkage or not in the loading matrices. So there are several possibilities here. I'm just going to go straight to what we do. So our goal was to extend DSS for the factor analysis, and that's what we did. That was the main theme. This slide is similar to some other speaker slides with the review, a basic review of factor analysis. So think about, the Y's here being the attributes in your particular area. One area that I work a lot these days is the Y's are stock returns for like a number of companies, like 100 for instance. And what you're trying to do is to factor the variance of this 100 assets as a function of, like latent factors, F. They could be represented by industry, regions, or countries, or things like that. And beta here, B, is the loading matrix that tells you how important those factors are in explaining each one of those N components, P components. So the traditional factor analysis, Gaussian linear factor model, essentially tells you that you're looking at the covariance matrix of the Y's now in a particular constraint. So instead of having P plus 1 divided by 2 components, you have PK components, order PK. So it's become linear in P instead of quadratic in P. So you impose a lot of restrictions. And in most applications, in most areas, if you have 100 time series, for instance, or you have 100 attributes, related to observations, chances are that the number of factors will be much lower dimensional, maybe 5, 10. So I don't remember in the last 20 years since I finished my PhD, finding any factor model application with more than 10, 15 factors. When you find 15, that's already a lot. Maybe you have 1,000 time series or 1,000 covariates. So it usually boils down to 2, 3, 4, 5, and there are reasons for that. Okay. So I'm going to skip through this because we all know, for the basic factor model, we all know the Bayesian approach. The most common one is to separate the priors for the loadings and the idiosyncratic uniquenesses, the idiosyncratic variance, and model this B matrix according to a lower triangular, positive lower triangular matrix, just for identification or rank identification. Okay. If you do impose more sophisticated priors for the loadings, that's fine. That will still be like reflected in the posterior distribution that we find down here in 4. The point is, once you fit your factor model or any covariance structure model, you plug that into here, and then now you maximize or you minimize this utility, this loss function, conditioning now on this omega. So that omega is the one that comes from whatever you learn from the data, so that is the shrinkage part of the estimation, and this omega tilde is the one that you're going to use to maximize. So you're going to find in the space of covariance matrices, that one that minimizes this expectation here. Okay. So in the Bayesian framework, we just take the prior distribution, and then you reconstruct this matrix omega according to which factor model you fit. Okay. So the expectations, you can derive this, you can prove, I'm sorry, you can show that this expectation can be written like that. So the expectation of this loss function. And again, let me stop here for a second. You can play with other types of loss functions. I'm just using like a log predictive loss function, but you could include more specific type of losses depending on the application you have at hand. If you're talking about DNA data or finance data or climatology data, you might want to change the type of penalty that you want to use. Here, we are actually thinking about a predictive penalty. So you want to, use the predictive distribution as your function to compare models. Okay. So with that, there is an E missing here. It's like a Monte Carlo approximation. We fit the posterior distribution for B and sigma, and then we reconstruct what would be like, the posterior mean for the sum of B transpose sigma, which is the covariance matrix of the Y's that comes out of that. So in summary, now this equation 7 is the most important one that we have here. When I show you the simulated exercise and the real data application, it's still a small application. What we're basically doing is thinking about a loss function, and now you can see that this part here of the loss function is the one that is trying to find the covariance matrix for the Y's that is as close as possible to the posterior mean from the saturated model, but also penalizing the loadings of the factor model according to, for instance, a norm 1 penalty. It could be some other type of penalty. You can generalize that, as I said. What you're actually doing there is to change the loss function. So the optimization scheme is the following. Fit your model, saturated model, find the posterior mean, plug that in here, and now search in the space of all factor models for indexed by K factors. So if you are thinking about, let's say, 20 attributes, you go from 1 to 20 factors. You know that 20 is not going to probably be needed, but you run K from 1 to 20. And for each one of those, you also index by this lambda function, more or less penalty. So if lambda, in this particular case, if lambda is 0, what's going to happen is that you don't penalize. What you're going to get is just, omega tilde just equals to omega bar. Like the posterior mode is the best choice. But if lambda goes to infinity, then what you're doing here is just like penalizing heavily the matrix of loadings. So the lambda will play a role here in terms of sparsity inducing, but not in the estimation, in the optimization, in the decision as part of the analysis. So, and this is something that Henrique did. He tried a couple of packages. He didn't code himself, so he used that one. We did a bunch of exercises. So you can use R, for instance, if you're doing in R. There are packages to obtain this minimum. So it's an easy job. So we get draws from the posterior. So here's the summary. It's like a recipe. We draw from the posterior distribution, estimate the posterior mean for omega. Then you run through K from 1 to K, like K tilde, and lambda in a set of potential penalty values. And then you find that one that minimizes the loss. So when we do that, we can plot these losses for different values of number of factors and different lambdas and decide where it starts to deteriorate when compared to the one with the saturated model. So if you think about the saturated model, it's like, I don't even care about a factor model. I'm just going to take the sample covariance matrix. So I want you to approximate that sample covariance matrix, which is unconstrained. I have enough sample size, like enough observation. So I want to find which factor model with sparse loading that best mimic the behavior of that sample covariance matrix. Okay. So that's what we are doing here. Okay. So I just want to show you like one example, a simple example simulated exercise. This is like, did I hear my feedback here? So this in this simulated exercise, we have only 2 factors. We have 8 variables, very simple, controlled. You know, this has been used this kind of example has been used by many people, including myself in my 2004 paper from my thesis. It's basically saying, well, the first factor, you know, it's important for the first 4 variables, a little bit important for the other ones, but the second factor is heavily important for the following 4 variables. So it's essentially saying like you have these orthogonal factors separating the 8 series or the 8 datas or attributes in 2 groups. The sample size is not that large, just 100, and we do like simple standard priors for the loadings and everything else. So we do fit a factor model as our unconstrained model. Okay. And then we do now from 1 to 5. So let me go back here. With 8 attributes, I don't need more than 5 factors. I cannot not actually identify more than 5 factors. So we go from K1 to K equals 5. And here we use 10 lambdas. So this is the picture, the summary plot that the DSS has for regression that we adapted here for the factor analysis. In the regression setup, this here will be the number of regressors. But for us, it's pretty natural to think about the number of factors. So this is basically saying that when I do a 5-factor model, I get results that are very similar to this bar here with the unconstrained factor model with, you know, the maximum number. As I move in that direction, I'm decreasing the number of factors and also varying the lambda. So you don't see any variation here because for all lambdas, you get exactly the same result, but not here and there. So as you degrade a little bit the number of factors to 2, you start realizing that, well, depending on the lambda, you get more or less sparsity. And one potential idea is to stop, that's another step to decide, stop at the number of factors that keeps the medium here, or the mode or mean, inside this 95% interval or 80% interval. So that red one is the one that we would stop. So in other words, you would, if I had to pick a number of factors in this example, I would pick a 2-factor model, and with some sort of sparsity for this data. Fine, this is a new object we can look at and decide about with these violin plots, you know, fancy box plots. But one thing we, as factor analysis researchers, like to do is also to observe the loadings to understand how the factors relate to the actual variables. So in A, we have the true loadings. You know, remember, like, these were like very close to 1 here and here and very close to 0 otherwise. And those are the loadings that come using our DSS factor analysis implementation. In one case, we, in one case we impose sparse loadings, potentially sparse loadings, and in the other case we don't. We just use DSS without that penalty component. So you see that this C is very similar to what we find in A, and B, these numbers here, like these values, are closer to 0, like forcing more, you know, sparsity a posteriori in the decision step of the analysis. Okay. I think I have a minute. We did a simulation exercise. I'm not going to go through that. I'm just going to go quickly just to show a picture. So we did like a bunch of replications just to show how different types of priors for the shrinkage part would behave. So here we have 3 different priors. Sorry. The Gevecki and Zuhl prior is the lower triangular prior, just Gaussian below the triangular constraint. Here's the unconstrained. You just ignore that there is any order, any zeros in the factor loadings. And there's this other one that's based on a recent research. The point is, depending on independently of which type of the priors you use, when you do like DSS, you usually get better results, or at least equal results when compared to marginal likelihood. Where marginal likelihood is just looking at the number of factors at the marginal likelihood of the factor analysis component. going to skip this picture. Here, when we do similar results, but now we make we change the size of the idiosyncratic component. So we have more noise or less noise. So depending on how much noise you have, or if it's a student T-distributed noise, you know, you start losing in all of these methods, but we lose a little bit less using our DSS. So by separating the inference aspect from the selection, you're actually like avoiding a little bit. It's something similar to what Ed did like in his example. Like if you have less information, so there's a lot of noise, it might be better if you do first estimation and then the maximization afterwards. This is one exercise. And just to finalize, we played around with two famous priors. You know, they appeared in these papers by David Dunson and co-authors over the years. Famous one like 2010 with this infinite prior, like a kind of Litterman type of prior for factor models. And a more recent one, this CUSP, the cumulative shrinkage prior. So we use two different priors, and we implement this factor model on a very well-known data that was analyzed by Dunson, but also by other people, not necessarily Bayesian, where they try to find these big 5 personality traits on a particular subset of the data. Only 25 personality variables about openness and other characteristics of 126 individuals over age 50. So we don't have a large data, only 126 observations. We have 25 characteristics. So the question is how many factors we come out of this analysis. And we run our MCMCs, and we get these kinds of things. And actually, let me go back quickly just to finish. When we run with the two different priors, we actually get the number of factors from one analysis equal to 21 factors or 2 or 3 factors. So completely different number of factors if you look at the marginal likelihoods for it based on each one of those two priors. So you have to be careful when you talk about the number of factors, because that is heavily affected by the prior you use, because you're doing the estimation. But when we do our DSS, you see that the idea that I presented in the simulated data is the same. So I just keep going to the left until I reach, the bottom. In other words, I need only 3 factors, which is something that Dunson also found in the paper, the original paper as well, that you don't need these big 5 factors in psychology, but only 3 of them. And we find that depending on independently of which type of prior we are using. In both cases, we are saying 3 is the number of factors that you would want to consider here. Okay, and you could look at the you could look at what is the output of the covariance matrix for those 25 components coming out of each one of those analyses. And they are very similar. In other words, even though we are doing this decoupling of shrinkage and selection, we are still recovering pretty much the same type of covariance behavior that you would have obtained have you done each one of these other methods. Okay, I think I'm going to stop here. I think I passed like a few minutes, but Ed also passed a few minutes. So like on the translation, it was just on that time. Okay, thank you.